Good afternoon, everyone, and welcome to Midas Technical Seminar. My name is Puya Banibayat from Technical Support of Midasoft. And as you know, today we have technical seminar on displacement time history analysis of long-span bridges, which is a part of our new e-learning courses, which will start this year in 2013. So e-learning courses is actually a way to communicate with the engineers and share the knowledge and information about the bridge engineering. So to whom are new to this session, I need to briefly go through these e-learning courses and explain what are those, and then we start with the presentation. So technically, e-learning courses is composed of 3 parts: technical seminar, case studies, and in-depth discussion, and numerical modeling and analysis training. So these 3 parts can complete a package of a learning package for an engineer to learn a new topic or new subject in bridge engineering. So the purpose of doing these e-learning courses is to contribute to our client as a part of technical services. We would like to provide as much technical services as we can to our clients. Then also we want to spread the technology through the sharing it with other engineers and bringing a happiness to other engineers and leading to breakthrough events. So quickly, I just touch each one and explain that what are these 3, and then what are the relation of these 3 and how they can be useful to the engineers. And the technical seminar is a session which professional engineers or professors or specialists from DOTs present a topic on their experiences, and then talking about a certain project, that how it has been done, and what are the challenges during that that project, which it could be design, it could be construction, or load rating, or any other type of projects. Then the benefits for this is that this session is an excellent opportunity for structural and bridge design engineers to get the first-hand information and knowledge about the design of a specific type of bridges. Like last month, we had network tied arch bridges, which our presenters, guest speakers from HNTB was explaining that steps of that design, the design of that type of bridge, and the challenges that the engineer or the designer may face during that type of project. So that will be useful for both people who have had such experiences or designed such a projects, which they can compare their results with or approaches with other companies, market-leading companies, and also for people who are new to this topic, they can learn a new topic in such sessions. So you can see a brief list of our guest speakers from universities, from DOTs, and design companies, both from Canada and from US. Then after that session, we have an in-depth discussion and case studies. This is a follow-up session, which the previous topic will be discussed more in detail, and we will be sharing a certain case study and sharing more detail about that project. Because there might not be enough time for the presenter to explain every single steps. So the steps of the design or analysis will be explained in the in-depth session, and so the engineer will learn the advantages of finite element for using being used in this type of analysis or design. You will learn the step-by-step design of certain type of project, or setting up the analysis for certain type of projects. So these are the example of type of bridges which we had in our previous sessions, and we will be talking about them more in future sessions. Then finally, all these sessions will be finalized by the numerical modeling and analysis training. So in this session, the engineer will learn how to apply those knowledge into the real life and how to do the modeling, how to perform the analysis, and how to extract the result for real design. So with these 3 courses, an engineer can have a good idea about how this type of project can be done from start. What are the challenges, and then what are the steps of the design analysis, and then how we have to do the modeling and get the result for the design. So it will be a complete package for the engineer. And we are using our software Midas Civil for doing this demo, and then showing you how you can use different type of element and also different type of analysis to complete this project. All right, so we actually have upcoming sessions, which I will be discussing about this at the end of the presentation, after Ben's presentation. And just let me quickly talk about our presenter today, and then turn it over to him, and we'll listen to his presentation. All right. As you guys know, today the topic is displacement time history analysis on the long span bridges, which we have Mr. Benjamin Szymanski from Parsons Brinckerhoff in New York office. Mr. Szymanski has a bachelor and master degree in civil engineering and structural engineering from University of Connecticut. And Ben has been working as a bridge engineer for more than 6 years, and he has experience in steel plate girders, tied arches, cable stayed, and truss bridges in United States. Most recently, he has been involved in value engineering and construction support of the Alexander Hamilton Bridge, which was a rehabilitation project. And so today he will be sharing his years of experience in bridge design and especially dynamic analysis of bridges with us. Okay, so I will turn it over to Ben, and we ask him to start the presentation. All right, Ben, you may start the presentation.
Okay. Just waiting for this to go away so I can maximize. Okay, so welcome to today's presentation. My name is Ben Szymanski, and I'll be presenting on displacement time history analysis. Okay, so just as a summary of what I'll be going over today, I'll start off by giving a history of seismic design in the U.S., just a basic, the abridged version of the history of seismic design. And I think to understand time history analysis, you really need to understand response spectrum analysis. I'm sure most of you that are listening in already are quite familiar with response spectrum analysis, but either way, I'm going to give a brief background on that before going into the theory and the background on time history analysis. So basically, I'm going to go over the basic theory, the applicability, and some of the advantages of using time history analysis. Next will be, where does the input come from for time history analysis? I think that's a lot of, there's a lot of people that are questioning where this data comes from. So I'll be talking about where the input comes from and then the software that can be used. And then finally, I'm going to show how a displacement time history analysis can actually be performed in Midas And at the end, I'm going to compare my results between response spectrum analysis and time history analysis. So I'll go over both of those in Midas. Okay, Puya already gave a pretty good background about who I am. I guess just to reiterate, I've been involved in bridge design and analysis as well as inspection for the past 6 years. I'm based out of New York City working for Parsons Brinckerhoff. I've been involved in a wide variety of bridge designs, which I think I'm pretty fortunate for that, as well as inspection of some pretty interesting bridges. I was involved in the Jamestown inspection in Jamestown, Rhode Island. It's a concrete segmental box girder bridge. The Newport Pell Bridge, suspension bridge in Newport, Rhode Island. I was involved in the emergency inspection for a number of truss bridges in Minnesota following the I-35W bridge collapse, as well as some steel plate girder inspections. Okay, so just to go and give a history here, very brief history. 1925, an earthquake takes place in Santa Barbara, California, and that's when engineers really start to look at adding seismic provisions for building codes. You're seeing that this is becoming a common occurrence, and there's just catastrophic failure. So how do you deal with that? Fast forward another 20 years, you're in the 1950s, and that's when we start having similar provisions being added to bridge design codes. I find this to be quite common. The building industry generally leads the way, and then the bridge industry will follow. We're seeing that a lot now with using BIM for our design. The building industry has been doing it for a number of years, and now the bridge industry is really starting to move forward with that. Okay, 1971, the San Fernando Valley earthquake gets Federal Highway to begin doing some research and starting a research program to establish criteria for seismic design. The picture I have to the left is some of the aftermath of that earthquake. As you can see, just catastrophic damage, and that really gets engineers and the agencies to start looking at this more closely. 1973, Caltrans begins developing new criteria. Caltrans has really been leading the way as far as the state agencies go and developing seismic criteria. They're really cutting edge compared to some of the agencies across the country. Okay, 1975, AASHTO adopts some of the criteria from Caltrans. And then in 1979, FHWA finishes their research program. So after this, AASHTO takes that research that Federal Highway did, and they establish guidelines to create the guide specification for seismic design of highway bridges. And I'm sure most of you are familiar, but a guide spec that AASHTO creates is more or less a guide for engineers to follow that is usually specific to a certain topic. So it's a little bit different than the normal bridge code that we're used to from day to day, but generally it's new cutting-edge topics that are created into guide specs. Okay, so 1986, provisions for seismic design begin to be included in the standard spec. 1989, the Loma Prieta earthquake occurs. The picture that I have to the left here is of the Cypress Viaduct. Now, this was a double-decker viaduct that ran through Oakland, California, and it was built on very poor soil. And what happened was liquefaction occurred. I'm sure most of you remember that from soils and geotech class in school. But so liquefaction occurred, magnified the seismic forces, and this bridge was built in the 1950s. So it wasn't designed to act as a ductile structure during such an event, and the second level collapsed onto the first, killing 42 people. So this really, underscored the importance of looking more closely at seismic design and how we can go and avoid such disasters. So in 1992, AASHTO guide spec becomes a national standard. And then in 1994, the Northridge, California earthquake takes place. That's the picture to the left here. And there becomes more of a focus on seismic retrofitting. As you know, most of the bridges in this country have already been built, and we're just trying to keep up with the rehab. So retrofitting becomes a really hot topic. So If you look at the picture to the left, you'll see that the mode of failure here was the piers moved longitudinally and the entire span dropped out. So ways that retrofitting are commonly done is they'll extend the bridge seat, or they'll add restrainers in order to keep the superstructure from more or less falling off of the bridge seats. Okay, 1995, the AASHTO Bridge Design Manual was released, which is what everybody's familiar with right now. 2001, the Seismic Retrofitting Manual is introduced, so that now there's actually a manual that people can use, engineers can use to follow to go and retrofit their existing bridges. For those of you that are from the Northeast, I'm from Connecticut, and if you drive along I-84 through Waterbury, you'll notice where the Route 8 connector is, there's a multi-level ramp structure, and those are all retrofit for with restrainers and extra reinforcing on the piers. So I think this is quite a common practice nowadays. 2007, the AASHTO LRFD guide spec for seismic design of highway bridges is created. And this highlights the transition from a force-based design, which we're used to in the AASHTO LRFD, to a displacement-based design. This is kind of understanding that in the event of an earthquake on a major structure, the structure is not going to behave elastically. Depending on the structure, it won't behave elastically, and we should probably be looking at more of the expected displacements that take place in a seismic event. So an example of a type of analysis that's done to look at the displacements is a pushover analysis, which is becoming more and more common. Now, this isn't to be confused with the topic that I'll be talking about today, displacement time history. My presentation is still a force-based approach. Displacement time history is still force-based. This is just simply looking at the displacements of the soil on the substructure in a seismic event. Okay, so looking at response spectrum analysis, just to give a background. So the definition of response spectrum analysis is a linear dynamic statistical analysis method. So basically, this method is commonly used in the AASHTO Division 1A and the current AASHTO LRFD spec that we're all used to. It was first introduced in 1932 by Maurice Anthony Biot at Caltech, and it's based on the theories of acoustics developed by Raleigh. So it started being extensively used in bridge design in the 1970s, as I previously discussed. Really, 1971 is where it's really started to be a big push for it. And the basic way it works is an eigenvalue analysis is performed to go and determine the mass and stiffness distributions across your structure. And your structure may be analyzed as a single degree of freedom system or a multiple degree of freedom system. So the overall goal here for seismic design in general, not just response spectrum, is to minimize any significant damage to your structural components. And they say small to moderate earthquakes should be resisted within the elastic range without causing any significant damage to the structural components. So that's really the name of the game here. Okay, so just a very basic overview of how the single degree of freedom principle works. I'm sure most of you have seen the old lollipop example where the top here we have the M represents the mass, our lumped mass of our structure, and then the stick at the bottom is our stiffness of our substructure, generally our piers, and which will vary longitudinally and transversely, obviously. And just using this equation here for the structural period can be very useful to go and do as a kind of a side hand calc to verify that your model is operating correctly. So your period that you find from this equation should be very close to what you're seeing for your primary modes in your model. So it's a great way to go and do sort of a sanity check on yourself. Okay, so response spectrum analysis in the AASHTO LRFD. So what I've got here is our flow charts that AASHTO provides you with to go and tell you exactly what you need to do in order to go and determine your seismic forces, build your response spectrum. Okay, so the basic premise of the current AASHTO LRFD is it's force-based, as I previously discussed. The flowchart that I showed provides you guidance for your seismic design. And using the AASHTO LRFD, you can use the uniform load method, which is can basically be done by hand calculation, or a multi-mode spectral method, which is basically what you guys will be doing using your Midas model. You're combining your mode shapes to go and find your envelope for your forces based on your earthquake. So in order to go and build your response spectrum, you're going to need your spectral acceleration coefficients, your site factors, ground acceleration coefficients, and your seismic performance zone. Okay, so response spectrum analysis and what the response spectrum that you create from the AASHTO LRFD is usually pretty adequate for most ordinary bridges. By ordinary bridges, I mean the bridge that's on the bottom of the page here. This is a simple highway overpass, you know, just a few spans, continuous bridge. Everything that's the maps that are in AASHTO are based on a 1,000-year return period, although many times the clients will ask for a 2,500, 2/3 of a 2,500-year return period. So that may also vary depending on the client. A site-specific response spectrum may also be generated if, depending on the site and the importance of the bridge and the available data, you might have a site-specific response spectrum that's generated rather than just the response spectrum that you create from the AASHTO. And you may also have a vertical spectrum defined. That all depends on the project. So simple span bridges are exempt from seismic analysis in the AASHTO LRFD. That includes any sort of analysis, although there are provisions within the AASHTO for simple span bridges to design in the event of an earthquake. Okay, so your response spectrum is created using your AASHTO site maps. The 2 slides ago I had one of the AASHTO site maps for the Northeast and then the tables that are provided. You need to determine the bridge importance category, and then you need to determine the modification factors to use based on what the operational category is. So whether it's a critical bridge, essential, or other, and that's the R factor that you'll find in the AASHTO. And those modification factors are applicable to your substructures and then connections to ensure that plastic hinging takes place where you want it to take place, basically. So you want to make sure that the plastic hinging takes place, as in this diagram shown at the top or bottom of your column, and not below grade where it's going to be really tough to get down there and repair your structure. Okay, so combining your member forces, you can use the square root of the sum of the squares method or CQC method. CQC is used for closely spaced modes, but either method is reasonable to use. And then also, in order to account for directional uncertainty, you would, since this is all an approximation, you would use 100 for the longitudinal force. You'd use 100% of your longitudinal plus 30% of your transverse, and so forth with your transverse force. Okay, now state-by-state seismic provisions may also vary. Some states have their own seismic provisions. So what I have shown here is the South Carolina DOT seismic design spec for highway bridges. So you'll see this especially in high seismic zones, Caltrans, California, Washington State. A lot of those West Coast states will generally have their own provisions as sort of a caveat or an addition to what's offered in the AASHTO LRFD. And this is just meant to provide further guidance beyond what's offered. And in some cases, what's included is a displacement-based approach. As I said earlier, it's becoming more and more common to look at these earthquakes as acting in the plastic range rather than acting elastically. Okay, so moving on to time history analysis. Okay, so it's basically an analysis of a structure, and you're applying your data over time increments, and it's a function of acceleration, force, moment, or displacement. Now I have a little graphic below showing what one of those functions would look like. Now obviously the closer you space your time intervals along your time history, the closer to accurate solution you'll get, but that's expected. So the picture I have to the left is the Cooper River Bridge in Charleston, South Carolina. And I know that was designed using pushover analysis, as well as, I believe, time history analysis. Okay, so time history analysis is similar to response spectrum analysis in that eigenvalues are generated on the structure based on a response to the time history. This is considered to be more realistic compared to response spectrum analysis, and it's most useful for very long or very tall structures, more or less flexible structures. Now there are some drawbacks for performing a time history analysis. For one, it's very time consuming. It generates and it also requires extremely large quantities of data, and in all cases it might not reduce your seismic forces. It depends on your soil property, structure type, and then you may not even be supplied with all of the data that you really need. So it all depends. Okay, so where does all of this data come from when we perform our structural model? So basically, soil springs and time history functions are generated by a geotechnical engineer. Depending on the size of your firm, it might be you. I work for larger firms, so generally we get our information from the geotech department. And the data can be generated either using 1D, 2D, or 3D analysis. So common software for 1D analysis is ProShake, and then you can use Midas GTS or Flush for 2D analysis. Those are also popular. So for a typical analysis, you would use the free field method for soil interaction, and that's basically looking at how the soil displaces based on your rock accelerations. And you don't need to model your actual bridge substructure in this case. With continuum analysis, that involves modeling both your soil structure and your structure together. So from that analysis, you would know the exact forces that are acting on your structure. For my example that I'll be using today, I'll be using a typical analysis. So what we're doing is we're inducing displacements on our soil springs that are interacting with our substructure. Okay, so I said that this is similar to response spectrum analysis in that basically you're still generating a response spectrum, but in this case it's defined at the rock level rather than at the ground level like we're used to. Forcing functions are then defined at the different levels along your substructure element, and it varies based on the depth obviously and then your soil properties. And then soil springs are defined along the length of your foundation which correspond with each of the forcing functions that you're determining. So that's either your forcing function is either a force or displacement. It all depends. Okay, so how is this data created? So your response spectrum, as I said, is defined at your rock level. And this can be done similar to what's done for response spectrum analysis, except as I said, it's going to be defined at the rock level. Now you can generate your response spectrum based on AASHTO, IBC, ASCE7, or USGS, and that's the map to the left there is a USGS map. And if you want to get even more specific, then you can do a site-specific seismic hazard analysis, but I won't go into detail with that. So from there, you would pick existing acceleration time histories which match your target response spectrum. So you would get a number of these, and you would use these as your different load cases for your time history analysis. Generally, you get a couple of these in order to make sure you're getting the actual worst case scenario. And the time history that you're grabbing should be for an area that matches the fault characteristics near where your actual structure is. Okay, now moving on to actually running displacement time history analysis in Midas. So for my example, I'm just going to use a fictional project. This is an elevated rail project, approximately 1 3/4 miles long. The superstructure is a composite plate girder. Hammerhead type piers, single column. They're 7-foot in diameter columns with 8-foot drilled shafts with approximately 120-foot long spans. Okay, now as I said, time history analysis requires large amounts of data. So we'll just pick out one pier for the case of simplicity here to look at. Okay, so looking at one pier, we need to go and find out what the mass is of our superstructure. So we can go and look at what sort of force would be generated from the superstructure if we look at it just on a single pier basis. Okay, so we can do this either by hand calculation or we can just run a static analysis in our Midas model. And from there, we can either convert that into a lumped mass and place it at the centroid of the superstructure, or we can use the loads to mass function, which is in Midas. That's what I'm doing right here. You can see that's the load from my superstructure, and then the loads to mass more or less turns that into a lumped mass that can be used to be placed at the centroid of your superstructure. Okay, so defining our soil springs. The way that you do it is you copy offset your shaft nodes at some arbitrary distance in both the x and y direction. For this example, I use 5 feet. And it's important to note that your offset distance should be more than your expected movement after the or during the time history analysis. But you also don't want it unnecessarily long where there could be computation problems. Also, generally in your response spectrum analysis, I'm sure most of you would make that bottom node of your shaft, either it's your point of fixity or where it meets the rock elevation. That's generally usually a fixed support. So you would no longer have it be a fixed support, and it would be a pin support. You would make all of your nodes that you just offset, those would all become fixed supports. Okay, so defining our soil springs. So the way that you do that is first you need to set your general link properties. And this is more or less setting your soil spring stiffness. Now, depending on your geotech analysis and the soil properties, also depending on if the soil is homogeneous, you might have different stiffnesses in either direction. In this case, for the sake of simplicity, we're going to have it be the same stiffnesses in both the x and y direction. So you need to use the general link function to define your soil springs. I know in the past I tried using the function for point spring supports, which more or less puts your spring directly on each of the substructure nodes. And for displacement time history analysis, that doesn't really work because as soon as you induce your displacements, all it's doing is displacing the structure by what you're telling it rather than displacing the soil around the structure. So that's what those springs really do, is simulate what the soil is doing. Okay, so adding our general link properties. So you need to be smart with how you name these. So for this example, my name here, I just named it 5 for being 5 feet below the ground elevation. Property type is a spring, obviously. And then my stiffness, which is just all I'm defining is my axial stiffness of the spring, which is under the linear properties here. And now I do this along my entire substructure, as you can see at the bottom here. Okay, so this is what they more or less look like. And then we need to go and define what the stiffnesses are and how they get attached to each of these offset nodes. Okay, so as I said, first we'll start off with a response spectrum analysis so that we have a means of comparing the two analyses. So I just defined my response spectrum. I'm only defining in the horizontal directions. I'm not defining a vertical response spectrum for this example. And then we need to go and define our load cases so that both my x and my y seismic forces. And this is being done using square root of the sum of the squares. As I said, it's perfectly reasonable to use that method. Okay, so our results. We end up with max bending in our drilled shaft of 7796 foot kips, bending about the z-axis, and 11,646 bending about the y-axis. Okay, so moving on to our displacement time history analysis. So as I said before, we need to go and define a number of load cases. So these are our functions that the geotech would define. So in this case, we're going to have 3 different load cases. You may have more. It could be 6, could be 8. It all depends. So this is how we define them. So for each, it may differ in time steps, but in this case we're going to make them all the same. So this is, the analysis type is nonlinear. The analysis method is direct integration. We have 50 seconds of total elapsed time. And then the time steps are 0.005 seconds, with the damping method using the element mass and stiffness proportional option. Okay, so defining our forcing functions. So as I said, we need to be careful with how we name our functions because we're going to need to combine these at the end. So on the left here, the L that I have in my function name represents the longitudinal direction that we're defining this displacement. S1 is the case, and then 5 is the depth below the ground level. Now, to define a displacement time history, we need to select normal under the time function data type. I'll explain how that works in a moment. Okay, so in order to use the displacement function, we need to specify unit displacements along our drilled shaft, and we specify unit displacement at each one of our fixed support nodes attached to our soil springs. Now we do that along the length of our substructure. Okay, so defining our static loads. Like I said, it's important that our naming corresponds with one another, so at this point is when you go and combine your loads and your functions together. So we perform our analysis, and this is our result. We end up with a max bending about the z-axis of 4,517 foot kips and max bending about the y of 5,086. So quite a large drop. So just to compare the two, about the y-axis we ended up with a decrease of 44% and a decrease of 58% about the z-axis. So as you can tell, there's an appreciable decrease in our drilled shaft bending moments. But this is not always typical, just as a warning. In this specific example, that's what the result was. But as I said, it also depends on your structure type, structure height, and length. Not really useful for ordinary bridges. Depends on the soil properties as well as many other factors. Okay, so in conclusion, what are the pros and what are the cons of performing time history analysis? Okay, so in some cases, as you saw, there can be a large decrease in bending moment in your substructure elements, which obviously will lead to a significant reduction in your steel reinforcement and possibly even your concrete quantities. But obviously that would require a whole other revised analysis because now you have different member stiffnesses. Now, especially in today's environment where we're seeing a lot of what would normally be design bid build projects are now becoming design build or P3 projects, a savings like this could mean the difference between winning a job or not, or just overall just saving the team the money for what it takes to pay for the quantities of steel and reinforcement for the substructure elements. So as I said, there can be a considerable cost savings by reducing the substructure quantities. However, the cons, not always applicable or maybe even insignificant for most bridge projects. For most ordinary bridges, response spectrum analysis is completely adequate. And then also, as I said, it's very time consuming and requires significant computing power to handle the data. I have a brand new computer, and even to run one bent, in some cases my computer crashed. So you really need to have a powerful machine to go and perform a fully robust time history analysis. Okay, so that's it. Thanks for tuning in, and if anyone has any questions, I haven't been checking if anyone has written in. Okay. So if you have any other questions, please feel free to email me at Szymanski@pbworld.com. Thanks.
All right, thank you so much, Ben. And all right, I just want to announce our upcoming events. As I mentioned in the beginning, we have follow-up sessions which will be completing the Ben's presentation. So we're going to have in-depth case discussion and case studies on the 15th, March 15th, and then we have numerical modeling and analysis training on 26th. So technically we're going to talk about the CAE solutions and steps for the nonlinear displacement time history, and then showing you how to utilize Midas Civil for displacement time history analysis for long span bridges, because really you can't do the displacement time history analysis with all software. You need certain tools. You need to define nonlinearity in your material and the boundaries, which not all the software can handle those. For people who attend the numerical modeling and analysis, if they are not the user, we will provide the free training software for number of people from that company who want to attend. So that's the opportunity to learning the software pretty well. Also, we will upload all the recorded video of today's presentation, and we'll upload it on the goodengineers.com. Please go to our website, goodengineers.com, and check our upcoming sessions, or you can just watch the previous sessions. All the videos and presentation files are uploaded there. You have access to them. You can go through and double check them. And for another technical seminars in March, we have two more, which we have guest speakers from Michael Baker. We have Dr. Ling Zhao and Dr. Diana Nevling, which will be talking about the response spectrum analysis and seismic design of conventional bridges. And Dr. Nevling will be talking about analysis of parameters influencing the curved steel bridges. So those are pretty interesting topics. Please join and enjoy and learn more about the bridge industry and bridge design. And we do our best to share all these information with all you guys. If you have any questions, please feel free to send the questions to us, or if you have any questions for Ben, he shared his email, Szymanski at pbword.com. So please feel free to send the questions, and we will be so happy to answer the questions. So I keep the session open. If you have any question now, we'll be here till 10 minutes, and I'll be answering those questions if it's related to me. All right, thank you. All right, there are several questions regarding the video recording. As I said, we upload this recording on our technical website, goodengineers.com. So you can go to www.goodengineers.com, and you have access to previous seminars, and also the current seminar. Actually, it takes time to upload it, but from tomorrow you have access to today's seminar as well.